The fifth presentation is the development of the object transfer robot with a variable height using pantograph-type jack system. The presenter is Mr. Kurasawa-san. Yes, please.
Can you hear me?
Yes, it's okay.
Thank you for attending this presentation. My name is Kazushi Kurasawa. I'm Tokai University student from Japan. I will explain the presentation through the development of the object transfer robot with variable height using a pantograph-type jack system. This presentation consists of introduction, objective, robot configuration plus operation, verification experiment plus discussion, and conclusion. A variety of mobile robots are being developed and applied in real life. For example, an automatic transfer robot, mobile LD, harvesting strawberry without damaging them, strawberry picking robot. Robots for factories equipped with robot arms, WH-HV5. Especially in Japan, the importance of robots is increasing due to the labor shortage and the promotion of remote work. However, there is a problem when we try to implement them in offices or small factories. This is the difficulty of grasping an object when it is located at a certain height difference. This depends on the range of motion of the robot arm, and if a lift is installed, it will be complicated by cost and management. The range of motion of the robot arm itself is shown in the figure. Basically, the robot arm can handle A, and an object transfer robot with a moving mechanism can handle B. However, it is not possible to handle C and D. If there is a mechanism with a variable height, this can be solved. In a simplified way, the mechanism should be as shown in the figure on the right. In other words, by adding a variable height element to the robot arm mechanism, the arm's range of support can be expanded. What we are proposing here is an object transfer robot that combines a robot arm with a pantograph-type jack, a lifting mechanism, to expand the arm's range of motion for the purpose of creating a cooperative environment between humans and robots. In addition, we propose a method for object appearance grasping using this robot arm. The reason for using a pantograph-type jack as a lifting mechanism is as follows. It is safe because no object protrudes above the lifting mechanism. Excellent responsiveness and stability. Easy to control in terms of rotation, horizontal movement. The overall structure is shown in the figure. It consists of robot arms and a pantograph-type jack attached to a robot with a moving mechanism. It consists of stage 1, when the moving mechanism is attached. Stage 2, which controls the pantograph-type jack, the lifting mechanism. And finally, stage 3, where the robot arm is attached. Stage 2, which controls the pantograph-type jack, is shown in the figure. And the jack is opened and closed by a by the rotation of long screw to raise and hold the robot. Each flat bar has two holes in the center of its side. Addition, it has a female thread and through hole as shown in the upper right figure. When the long screw is rotated in the direction of arrow, the flat bar moves horizontally in the direction of narrowing in the center, which closes the lower part of the pantograph-type jack and pushes up the gripping part. On the other hand, when the grasping part is lowered, it is rotated in the opposite direction of the arrow. The pantograph-type jack enables the robot to move up and down within a range of 700 mm, which is 110% of the range of the conventional robot arm. It's hard to tell because the movement is slow, but in the video, the pantograph-type jack is falling. The moving image's robot arm is shown in the figure on the right. We will also talk about the object grasping system by the robot arm. The specification of the robot arm on stage 3 are as follows: 6 POS, 0.5 kg payload, 480 arm length, 3.2 kg weight. The robot grasps the object using a template based on the target object image. The other method is to use 3D models of the object to be grasped. But this method is superior in that it requires less time and effort to prepare the 3D model of the object. We consider grasping a target object by a robot arm in the following flow. The object to be grasped is photographed beforehand and the template image of it is created. The grasping motion is also pre-programmed using the starting position as the starting position. When grasping an object, the prepared template image is compared with the position of the image taken by camera mounted on the robot arm. And if it matches the starting position, the pre-programmed motion is replayed. In other words, the positioning is done based on the template image. This kind of operation eliminates the need to prepare 3D models with target objects and require less effort. This template image is prepared by taking a picture beforehand with the camera mounted on the robot arm. The movement of the robot arm to grasp the object is also programmed. Akaze is used to acquire 3 feature points, and 3 feature points are used to recognize and grasp objects. First, an image is acquired from the camera, and the closest teaching image to the 3rd feature point, the image is found. Then we calculate the amount of change in the 3rd feature point from the image and adjust the arm according to the amount of change to get the same view. Adjust the position of the arm, and when the image view matches the template, replace the pre-programmed movement and grasping. As a verification experiment, we tested the operation of a lifting mechanism and object grasping by appearance. For the experiment of the rising and the falling mechanism, we set the rising to 80 mm and the falling to 345 mm. This shows the rising and falling. As a result of this, we are able to confirm an increase in the arm's range of motion of 13% and 64%. However, the pantograph-type jack, when falling, showed a bit of instability due to the large force distributed laterally. We believe that this can be solved by installing a motor with higher torque and adding gears to regulate the motion. I play a video of the process of grasping an object as shown below. It's hard to tell in this video, but robot now adjusting the position of the camera image to match the template image. In the experiment of grasping an object with appearance, we success in adjusting the position and grasping the object. All objects are successfully grasped, but some objects may not be lifted depending on the object being grasped. This was due to weak grip strength of this robot arm. But we were able to confirm the operation of the object appearance. Now that the position was adjusted, it started the grasping motion. Keep grasping. This time, we propose a method for extending the range of object transfer robot by using its lifting mechanism, and the method for the robot arm to grasp objects by appearance. As a future prospect, we are considering the realization of automatic driving to a point of destination. Thank you for attending and listening.
Thank you for introducing the unique robot. Thank you very much. So, do you have comments or question from audience? So, okay, I have one short question. I think the robot is needed to so kinematics or inverse kinematics, including the pantograph mechanism. So have you derived this equation for the robot? Not only manipulator, but also including pantograph mechanism for
kinematic with pantograph?
Kinematic or inverse kinematics equation. Have you derived? Or are you going to derive to catch the object?
We decided to use a pantograph jack because it to be very easy control close and closed system. So
okay, maybe I think you use a so camera to reach the object. Maybe so it doesn't need to the so inverse kinematic, I think. Yeah, okay. Thank you. So
my robot arm kinematic is my papa is free.
Okay. Thank you. So, any other question? Comment? Okay. Thank you very much.
Thank you.
Thank you very much. Okay, it's time to go.